Starting with the introduction, in a solid system, as we all of you know, these solids are made up of the atoms closely spaced together. So whenever these atoms comes closer and closer, their electronic structures get shared with each other, and because of this sharing, the atomic atomic system or solid material becomes an electronic material. So depending upon the how this conduction phenomena takes place in the solids, there are three different types of the materials. So whenever these electron structures, as we all of you know, in atomic structure there is a nucleus, and around the nucleus there are different energy levels of the electrons. So as we go to the higher, electrons get the higher energy. So whenever these atoms close space together, the energy states are overlaps each other, and energy band structure is created. So in this figure, we will see the energy band gap structure of the solid materials. So this lower band is called as valence band. At the absolute 0 degree Celsius, this valence band is completely filled state. That is, all electrons getting attached to their respective energy levels, and this is called as conduction band. So conduction band at the 0 degrees Kelvin is always seen to be uh, in case of semiconductor material, it is empty. So depending upon this conduction band and the valence band structure, there are three type of the materials. In case of metals, the valence band is gets over almost overlap with the conduction band, and because of that, all these electrons are available, freely available in the conduction band, and because of availability of plenty of electrons, metals acts as a good conductor of the electricity. In case of the insulators, this energy band gap between conduction band and valence band is so high that at the room temperature also there is a very less probability or almost no probability to electron get excited from the valence band to the conduction band, and because of empty states in the conduction band there is no probability of the conduction in case of insulator. Whereas when we think about the semiconductor, the energy band structure or energy gap in the semiconductor is in between these metals and insulator. So this energy gap is can be utilized for switching application whenever we give some external stimuli. This external stimuli like thermal or voltage. There is a probability that electrons from the valence band can jump to the conduction band, and these empty states will get filled with the empty states get filled with the electrons which are utilized for the conduction of the electron. So always keep it in mind, whenever electrons get excited from the valence band to the conduction band, there is a white space created here of that electron. That white space is called as hole. Holes can be holes can be considered as a positive equivalent of the charge charge to the electron. So the lowest energy level of the conduction band is called as EC here, and the highest energy level at the valence band is called as EV. So at the 0 degree Kelvin, that is absolute zero temperature, the EV is the highest energy level in the valence band, where EC is the conduction band, lowest energy in the conduction band. So the difference between this conduction band and the valence band is called as energy band gap, EG. And there is a energy level is called as Fermi level. Whenever at the 0 degree Kelvin, we'll see in the further slides that at 0 degree Kelvin, the probability of finding of electron below this energy level is 1, and probability of finding of electron above this energy level is 0. So this particular characteristic energy level is called as Fermi level. Depending upon the situations, we engineer this Fermi level of the semiconductor material, and we utilize these properties for different electronic application. So we see the energy band gap in stats that in metals there is almost 0 electron volt energy band gap is there. In insulators, it is more than 5 electron volts. So it is very difficult to achieve this kind of energy to excite electron from the valence band to the conduction band. So almost there is no conduction in the insulators. In semiconductors, this energy band gap for silicon is 1.21 electron volt for 0 degree Kelvin, and for germanium is 0.785 electron volt for the 0 degree Kelvin. So this is again energy bands, energy states are available over here. All energy states are empty, whereas in this valence band, all energy states we can see there are 2 electrons. So there is a Pauli's exclusion principle which says that there are no 2 electrons allowed in any energy states. In every energy state, there are only 2 electrons are allowed. So in each energy state, we see that there are pair of electrons available. So whenever we get some external thermal energy or apply any voltage, these electrons will get to the conduction band. So there are different techniques. We can add impurities in this one and add this excite this electron to the upper level. So we will now derive the conductivity equation. Conductivity equation for the any conducting material. So this is a piece of conductor. So deriving this conductivity equation, we'll go to the find the how to calculate the conductivity of a semiconductor. So this is a piece of the metal of having the cross-sectional area A. Let's say total number of electrons available in this are equal to N, and the length of this conducting element is L. So total number of the electron passing through any cross-sectional area is equal to any cross-sectional area. Like let's see this is A is the one cross-sectional area. There are n number of cross-sectional area. Therefore, at any given time, total number of electron passing through any cross-sectional area will be total number of electron divided by time. So considering Q is the charge of the electron. All of you know that the charge of an electron is in coulombs, and it is very less, 1.9 minus 19 coulomb almost. So this charge of charge on each electron, let's say Q, then if we see the total number of charge going through any cross-sectional area at a time is given by NQ by T. This charge passing through any cross-sectional area per unit second is nothing but the current. So we can also write the I is equal to NQ by T. So as we know, we are going to find the current density. Current density is nothing but the current passing through any cross-sectional area. So J is equal to I upon A, unit is amperes per meter square. So inserting this above equation just now we derived, that the equation will be readjusted into this one. We'll get J is equal to N. N is nothing but the number of electrons. Q is the charge on each electron. T into A. So let's see how we'll come to the conductivity equation. So average velocity. So whenever we consider this is a conducting material, whenever we apply a constant electric field, so these all electrons will flow towards the positive terminal, as electrons have the negative charge. Electron will naturally attract toward the positive charge. So the velocity of each individual electron can be given by total length of the electron has to pass this total length L divided by time. So velocity of electron, or in we say whenever we apply the electric field, this is drift velocity, L by T, and this T is given by time. We can readjust that T is L by V. So we use this T equation in the previous current density equation, rewriting the current density J is equal to NQ, velocity of the electron, divided by LA. By looking at this equation, length into area is nothing but the value. So we can see here is N is the number of electron, LA is the volume. So number of electrons per unit volume can be written as carrier concentration. So carrier concentration is N by LA. So this N is considered carrier concentration. So product of the length and the area is nothing but the value. So this is a this can be again written into the above equations. Total charge in a given volume density rho is equal to NQ upon LA. Here N upon LA is nothing but number of electrons in a unit volume, that is nothing but the electrode concentration N into Q. The total number of electron concentration into Q, NQ, is nothing but NQ is nothing but the charge density. So charge density, we can again NQ can be considered as the rho. Rho is nothing but the charge density. So ultimately we arrive at an equation that current density of a conductor, any cross-sectional area, is equal to charge density into velocity of the electron passing through that area. So what is the mobility? Mobility is very important factor whenever we think about the semiconductor, conductors or material. Because in semiconductor and conductor we have the charge carriers passing through any 2 points. So mobility, if we let's say a solid system in which we apply a constant electric field against that substance, whenever we apply any electric field, and let's say this material is conductor, the electrons definitely going to start uh, carrying the charge. So electrons going to flow from negative to positive, that they will attain at a constant electric field, they will attain definitely a constant velocity. That velocity, therefore we can arrive at an equation that velocity is directly proportional to the applied electric field. So this proportionality has a constant. So that constant we can write V is equal to, that is velocity of electrons or velocity of any carriers, is equal to mu into epsilon. That constant of proportionality mu is nothing but the mobility of electrons. So mobility of the electrons is given by meter square from Goldseeker. So mobility of electrons or mobility of any charge carriers, in case of semiconductors we have electrons and holes or both charge carriers, plays very important role in calculating the conductivity. So we can again go through the previous equations, like J is equal to NQ into mu epsilon, because at the velocity of electron we get to this new relation, that is mu epsilon. So J is equal to N2 mu epsilon. So J can be written as, this is nothing but we also know the property of uh, from the electromagnetic fields theory, that current density is equal to conductivity into the electric field. So comparing these two equations, we get the equation for the conductivity. Conductivity is equal to NQ mu. This is for the metal. So sigma is nothing but the conductivity of the conductor, which is contribution of the charge carrier, that is here in this case electron concentration, charge on electron, and mobility. So we can directly say this mobility will be the constant for any given system, any given same material. Q is the charge on the electron. So both these are the constants. We can directly say that conductivity is directly proportional to the carrier concentration. So more the number of carrier concentration, the more will be the conductivity in the material. So in case of this mobility, uh, uh, equation or unit of the mobility is meter square per volt second. So for electrons, this mobility is given by for electrons in silicon mobility is 0.40 and holes in silicon mobility 0.05. So we can say that there is almost 3% extra mobility for electrons compared to the holes. Mobility in the germanium is 0.39 and for holes it is 0.19. Comparing the mobility of electrons in silicon and germanium, we can see that germanium has a much more higher mobility. So germanium conductivity will be much more at the 0 degree Kelvin. Sorry, at the room temperature. So how this conductivity equation can be utilized for the semiconductors? In case of semiconductor, as we all know, let's say silicon, which is a intrinsic silicon, will be having the two type of the charge carriers. So there will be the electrons available at room temperature in the conduction band, and because of absence of that electrons, holes are created into the valence band. So there are two types of the charge carriers available for the conduction. So we have to consider in the previous equation that developed for the current density, we have to consider the mobility of the both type of the carriers as well as concentration of the both the type of the carriers. So this equation for the current density will become now uh, as n q mu into epsilon. Now we have two more factors in this one, that is charge that is charge concentration of electrons and charge concentration of the holes, as well as holes and electrons have different mobilities, so we have to consider the mobility of this one. So the current density for the semiconducting material can be written as using this equation n mu n plus p mu p qv, where mu n is the mobility of electrons, mu p is the mobility of the holes, n is the electron concentration, p equal to. So as we know that J is equal to sigma E, so conductivity for the semiconductor material is given by sigma is equal to, that is conductivity is equal to n mu n plus p mu p into q. So conductivity again in semiconductor, intrinsic semiconductor is directly proportional to the concentrations of the hole as well as concentration of the electrons. So there are different types of the phenomena happening whenever we add the impurities in this one. So we'll discuss all this in the coming part of the lecture. Thank you very much.